great pleasure to have with us Bradley Ayes, that is an assistant professor of computer science at the University of Colorado Boulder, where he runs the Collaborative AI and Robotics lab and serves as co-director of the University Autonomous System Interdisciplinary Research Team. Brad's research develops techniques to create and continuously validate autonomous systems that both learn and teach and collaborate with humans. And the main aim of his work is to improve coordination, empathy, and capability at scale. So his work primarily leverage novel approaches at the intersection of human-robot interaction and explainable artificial intelligence. And he wants to extend the capability of robots in order to make them generalize skills while limiting the risk and acting safely in the environment. So I will now let Bradley introduce his talk that will be about multimodal planning and communication for human-robot interaction that is safe and collaborative. So please stop sharing my screen.
All right, give me one moment while I get my screen share set up. All right, looks like we are in good shape here. So thank you very much for the great introduction. So I'm very happy to be here to talk a little bit about some of the work that my group has been doing over the past couple of years. And so this talk is titled Multimodal Planning and Communication for Human-Robot Interaction that is Safe and Collaborative. And while I'm going to talk to some of the different algorithms that we've developed and some of the different systems that we've built, of course, the real core of this talk has to do with some foundational aspect of human psychology, right? And how people interact with these systems, because it doesn't really make any sense for us to build systems without understanding how people are going to use them, because if we don't have that, then we really have no control over what's going to happen when we really deploy them. And I think I speak for most of the human-robot interaction community when I say that it's one of our core interests to actually get robots out into the world, acting in beneficial ways. And this is something that is a huge hurdle for the robotics community that we're trying to contribute towards. So I'm going to talk about three different related ongoing research efforts, all kind of centered around explainable AI, and some of the journey that we had in trying to scope these projects. So I'll try to give as much flavor beyond the contribution in the paper as I really can. And of course, like with any of these talks, when I talk about our group's work, I primarily am talking about the phenomenal graduate students that make up the Collaborative AI and Robotics Lab, pictured here. So I'd like to start by just introducing the concept of value alignment in artificial intelligence. Now, this is something that's been around for decades, but has been going through various rebrands as the years go by. But the premise is roughly the same throughout. So value alignment seeks to help us ensure that artificial intelligence systems we build are aligned with human values and goals. Now, that is a little bit self-referential. And so I would say our challenge here is to be able to develop autonomous systems that can behave in ways that are beneficial to people, aligned with our values, while avoiding unintended negative consequences. So it's no coincidence that most of the doomsday scenarios that come up when people talk about artificial intelligence or robots happen to be runaway optimization problems. And so we've learned from quite a bit of experience empirically as a field that coming up with these optimization criteria, coming up with these solutions that reflect our values in a way that we're happy with is quite a difficult feat. And so I would say that one of the core research objectives of my group is to investigate and surface insights into human behavior, and then also develop the technologies that are going to help us ensure that the algorithms, optimizers, optimization criteria rather, and the emergent properties of the complex systems that we deploy use acceptable approximations of our values, including things like safety, fairness, transparency, and privacy. All of this, which is to say, We want to be able to look at the systems that we deploy into the world and say, particularly for learning systems or systems that are learning from information that we're giving them, did the system really capture my intent? And as a sort of high-level approach to this, the one that my group in particular takes into account is that we're trying to arrive at responsible autonomy. And for us, that means trustworthy deployments. So the deployment of this technology must be value-aligned and beneficial. And the way that we get to this is by looking at safe technology, meaning there's shared expectations across the behaviors of these systems, so that at the very basic level, these things are behaving in a safe manner, as well as shared expectations around decision-making. So these systems should be understandable as well. And only once we have these two foundational layers can we even start approaching something that we would be satisfied with as a trustworthy deployment or responsible autonomy. Now, Voltaire is credited with giving us the aphorism that perfect is the enemy of good. And in human-robot interaction, making system that is just good can tend to have a traumatic implication. And as we've seen now, artificial intelligence and machine learning is really just starting to get good. So it's very easy to look at some of the more compelling examples of autonomy. So on the left, I have the kind of summary video that Microsoft just released where they attached the ChatGPT up to automation to do some really impressive things. So language guided robot behaviors. And then of course, in the middle, we have one of the great clips from Boston Dynamics showing some extremely impressive robot acrobatics. And we could start to get to the maybe false conclusion that these systems are ready for prime time, that these systems are ready to be safely deployed into the real world. But as we've seen time and time again with certainly autonomous vehicles, we're not really prepared for behavior in the long tail of situations that these systems are really going to find themselves in. And this isn't because somebody did something wrong necessarily deliberately, but of course, this is something that we don't want to have happen, and we need to cover these kinds of situations. And so one of the core aspects of explainable AI that we're looking at is how can we get some kind of insight into the systems that are going to be operating in human-populated environments? So the first paper that I want to talk about today has to do with using coaching as a mechanism to take an expert system, so in this case, the Sawyer robot on the right, and using it to teach a person how to be better at something. And so we want to be able to come up with some kind of formal framework here that's going to allow a robot expert to identify a disconnect that a human might have about the domain or about the behavior that they're doing, and then provide corrective feedback to them through semantic formulation. So we know that learning from experience can be expensive. This tends to be a little bit more expensive for robots than for people. The natural end state of an exploring robot is, of course, to break itself. You might make the same kind of framing for people. And so we don't necessarily have to experience things in order for us to learn from them. Sometimes it's just enough for somebody to be able to give us a perspective on our world model that gives us the opportunity to update our behaviors accordingly. And so one of the core insights with this work was, if we can get a system to do very well at a task, then there's presumably some mechanism that we can tap into to have this system apply its perspective on your behaviors and try to use your behaviors to figure out what your perspective on the world looks like, and then take the difference between those to figure out where a disconnect might occur, and then come up with some kind of communicative act that is able to repair the difference between those things. So in other words, if we make some foundational assumptions that humans are goal-directed and generally rational, and they're just trying to maximize their expected reward, then if we as the expert AI system here are seeing something that looks confusing, then given these assumptions, the only conclusion that we can responsibly reach is that, well, they just understand the domain differently than we do. So they're following a different reward function. And if we were to maybe make this into a little bit more of a formal terminology, we can say that humans have a policy learning algorithm that generally works. And any kind of unexpected policy that we're seeing from this human indicates a difference in the reward function. And so if we want to improve their behavior, right, subject to our understanding or our expert opinion on what should be done, then we just need to augment and or repair their reward function. And so in this paper, we introduced a technique that we called reward augmentation and repair through explanation. And the gist of it is as follows. So if we have a representative domain like this, the optimal path would be to go to the top right, take the terminal reward at the +100 cell corresponding to R2. But if we saw somebody that was going through this domain and instead they ended up in the top left, well, at this point, we would presumably say that, okay, so given my assumptions that this person is rational, is trying to maximize their reward, they're goal-directed, the only reason they would go and get this 10 reward is if they didn't know that the 100 reward existed. And so we wanted to build an algorithm that is capable of recognizing this disconnect and then doing something about it to improve the human's performance. So the high level of how this technique works is that our autonomous system is going to try to estimate what the learner's reward function is, mostly just looking at what they do, and then assuming that they're following a policy optimal for that reward function. And this means that we're going to be tracking a belief distribution over the space of reward functions. Now, there are a ton of different ways that you can do this. Obviously, there's an infinite space of reward functions. We make some fairly convenient assumptions in the paper to make this a more tractable problem, namely that the learner might not know about all of the different rewards in the environment or the reward sources in the environment, rather than having misconceptions about false rewards in the environment. But you can subsample from this space as you'd like to still get the same effect out. And so what the system is doing now is keeping a tracking belief over all those different reward functions that the learner is likely to be following. And then once we get to a particular critical point in the trajectory where not only is there a divergence, but a divergence that will result in a significant deviation in expected reward, it will figure out how to intervene. So to put this into an example, let's say we're watching an agent work through this grid build from before. We don't really know if they know about any of the rewards in the domain yet, but they take a step forward. Our belief that they know about R1, R2, or both of these rewards would reasonably increase. And then as soon as we see that they take this left turn, our belief that they know about R1 should be very high, and our belief that they know about R2 should be very low, because any policy that includes R2 will not include this left turn. And so we have a couple of options, but we need to make sure that we communicate this particular reward before they make the next action. Otherwise, they're going to end the episode. And so in this work, we looked at two different options. So the first one was just saying, hey, if you do this next action, you're not going to get the best reward that you can get. So we don't tell them where the other reward is. We just say, hey, this is suboptimal. There's a better thing for you to do, and encourage maybe them to engage in a bit more critical thinking to figure out where the disconnect might be. The other option is to be more explicit and justify this action by saying, hey, don't go north. If you do that, you won't get the best reward. There's a better reward in the top corner. So something that actually says, here's where this reward source is in your state space. I'm not going to tell you how to get there. I'm just going to tell you where it is, under the assumption that you'll be able to update your reward function and run your policy convergence algorithm, essentially figure out how to get there on your own. And so we were trying to figure out which one of these options was going to make people more effective at a difficult task that maybe they weren't terribly proficient at. So in order for us to actually test this coaching algorithm, we had to come up with a game for people to play with the robot that people were necessarily bad at. And so we came up with a complicated game that we called real-time color Sudoku, where people were playing a game currently with the robot, placing these colored blocks according to certain rules that restricted which ones they could play when, and then added a bunch of confounding factors into the game that made it very difficult to predict forward. So the rules for real-time color Sudoku are as follows. So each player in the game has 3 rows to fill, and you will fill yours near to far, right to left. The robot has 3 rows in the back, but there are no turns. So you get to just play your piece whenever you're ready, whenever you have an idea of what you want to do. Now, just like in Sudoku, there were a couple of constraints to make things a little bit more difficult. And so we had a constraint where no color could appear twice on the same row. So you had more of a local constraint that you could follow. People are generally very, very good at this one. And then there was a neighborhood constraint that said that no color could border itself. This one was a little bit more difficult because as the robot starts playing, it's essentially making choices about where your third row blocks can be, right? Because as the early rows influence the later row in the interface between your blocks and the robot's blocks get much more obfuscated. It's much more difficult to actually figure out which block you should play there. And as a result, there are many, many dead ends. So we wanted a game where people would constantly be faced with these dead-end decisions and then be reliant upon an expert coach to actually help them out. So we applied our algorithm, reward augmentation and repair through explanation, to this game. So we briefed the participants. We told them that the robot was an expert at this game, which was true. We trained the robot to play it perfectly. And we also told people that the robot was on their team, that this was not a competition between them and the robot, but rather that they were working together to complete the game. And as a result, we saw in our hypotheses most of the things that we'd expect to see. So in particular, participants found the robot more helpful and more useful when it explained why the failures occurred. They found the robot to be more intelligent when it coached them versus a control condition where it didn't. But really, we were most interested in the objective hypotheses for this work, which was related to the people will complete the game faster when provided with the justification. So where is the reward that they should go find? But we couldn't even test this hypothesis because most of the participants didn't even listen to the advice when the justification wasn't present. They just ignored the coaching advice entirely, went their own way with playing the game, and then subsequently would lose. And so this was a really interesting result because we had seen a lot of examples of overtrust in the literature, but in this case, we were confronted with undertrust. And we happened to just maybe get lucky and find that this justification was a key part of people's decision-making rationale for why should they trust this system, even though, again, they had no reason not to trust it, and they were explicitly briefed in a way that would help them to find that trust. So the next work that I'd like to talk about was work that we presented this past year at AAMAS, where we looked at the kinds of guidance that we could provide to humans in a human-robot teaming situation to act not just as decision support, but also as a multi-agent planning problem, or to help solve the multi-agent planning problem. And as motivation, we looked to this avalanche rescue scenario, where you can see in the bottom right, you have 4 humans that have probes that are looking for victims buried under this avalanche. And then towards the middle of the slide, you can see people walking around with beacons that are looking for signals of people that could have been buried. So you have a latent signal that's that you can pick up with a sensor. And then you have heterogeneous capabilities. So the people that have the probes really are the only ones that can confirm a detection and find somebody to dig out, whereas the other people are moving around running these detections to try to get a better sense of the actual layout of where the goals are in this environment. And what we'd like to be able to do is recognize that this is an opportunity for robotics to improve the performance of the human team, for example, by replacing the emergency responders that are maneuvering around the debris field, because that is something that is quite difficult for a person to walk around and do, but quite a bit easier for a quadcopter to fly around over larger length scales. But of course, those quadcopters can't dig out victims. That's something that, at least for right now, is best suited for the humans. And so now we have sort of the required components for an effective human-robot team. But it doesn't make any sense to do this until we can make sure that the team actually works together effectively. So we built a system that would facilitate this human-robot teaming from a planning and decision support perspective. So we entered into this knowing that people overtrust decision support systems in general, in research that we've done and that plenty of others have done in the HRI community and beyond, have shown that providing action recommendations without any kind of backing information promotes overtrust. And so here, there are just 2 quick articles about essentially people overtrusting Google Maps, even though it overrides their common sense somehow to drive their truck into a river or end up stranded with hundreds of other people on an empty field. So obviously, we want to avoid these kinds of things. We don't want people to do unintelligent things just because they're teamed up with robots that maybe they think are intelligent. So we developed an algorithm that we called MARS, the min-entropy algorithm for robot-supplied suggestions. This is an algorithm, as I mentioned, that was targeted towards domains like this avalanche rescue scenario. So you have human-robot teams with heterogeneous capabilities. There's communication between these teams available. There's partial observability. And there are multiple goals in the environment. So we might be trying to find more than one target to rescue here. And so we loop the humans into this multi-agent problem through augmented reality with three possible communications. So one is that we looked at is visualizing action recommendations. So we call that prescriptive guidance, telling them what to do. Latent state feature visualization. So this is descriptive guidance, giving an overview of the factors that went into providing that prescriptive guidance so that you could make your own action choices. And then a context-grounded action recommendation visualization where we combine both the descriptive and the prescriptive guidance. Now, in general, the workflow for Mars looks like this. And so on the top and bottom of this figure, you'll see like a grid world where there are cells that range in color from dark purple to bright yellow. And in this case, dark purple represents a high entropy state, meaning that there's a 50% chance that there is one of our goals hidden in that state and a 50% chance that it's not. So we don't really know much about that versus a state that is yellow, which means that we have a high confidence that one of our goals that we're trying to find is in that state. And so what we'll be doing here is sharing this probability mass function across our state space with both the human and the robot sides of our team. We're going to solve Markov decision processes for each of our agents online to figure out what we should have them do as our information updates come across. And most importantly, when it's time for the humans to act, we want to make sure that we communicate what they should do through an augmented reality interface, because of course we can't make actions for the person themselves. So here's what our walkthrough looks like of the algorithm. So we first initialize our shared probability mass functions. This is our prior belief of maybe where our targets are. We solve for the robot's actions. So in this case, the robots are trying to minimize the entropy over this state space. So they're trying to take observations and help collapse the probability distribution over where these goals might be. The robot takes an action. The robot gets a new observation. We update the probability mass field with this new information. Now, of course, the person can't see any of this yet. We solve an MDP for the human to figure out if we did actually have control over them, what's the best thing that they could do. Then we have to somehow convince them to do the right thing according to our algorithm, so show them the information that is most beneficial to them making an informed decision. We see what they do. We get the reward from the action that they're taking, update the probability mass function, and then repeat this cycle until we complete the scenario. So what this looks like in practice, we have our prescriptive guidance condition visualized here. So again, this is just a sequence of arrows. If you're a fan of Daniel Kahneman, this looks like system one thinking. So there's nothing for you to think about, just opaque recommendations. Go follow the arrow, open up the box to see if you found your goal. And we contrast that with descriptive guidance, where now we're showing visualization of that probability mass function for each of the states. So you can see like where the system thinks that there's high likelihood that one of our goals could exist. And this, of course, would correspond with system two thinking, because it's slow, effortful, conscious. You still have to come up with your own plan, but maybe you're now empowered with some additional information to make this easier for you. So rather than have people run through the avalanche rescue scenario, given just the space that we had available to us, we used a Minesweeper analog to this. So it has pretty much all of the same components, except with the caveat that in this game, if you step on one of the goals and then you leave without actually achieving it, we give you a big negative reward. This is analogous to missing an avalanche victim as you're searching. And so participants would collaborate with a drone to take measurements of the scene, find the path, and as you can see in this interface, they were able to navigate through this field. Now, they could have just opened every single box that they came across, but this would take a huge amount of time, and nobody did that. So we succeeded at least in figuring out an experimental paradigm that really accentuated the things we wanted people to do in this collaborative domain, and to be able to productively operationalize this information. So we had people participate in this study. It was a 3-condition within subject design where everybody saw a prescriptive case, a descriptive case, and a combined guidance case. And when we looked at all the subjective results that we got, we saw pretty much all of the things that we would expect, that this information was getting used properly. So for example, people really liked combined guidance, so prescriptive and descriptive. Over the other cases, they found it was more interpretable and helpful for decision-making, which makes sense. We're giving them more information. One of the things that surprised us was that people found prescriptive guidance to be quite taxing. Now, there was no additional information for them to use, so there wasn't really anything for them to think about, but people still tried to reason their way through something without any of this additional information. And so that was a bit of a curveball for us. And then one of the things that we thought was most interesting was that the combined guidance empowered our participants to act with more independence versus prescriptive guidance. Now, this makes a little bit more sense for us, but it also was unexpected that they just wouldn't follow the prescriptive guidance that was given to them. But the thing that was maybe most interesting with that, if we look at these charts on the left, we can see performance as a function of how much they complied with the prescriptive guidance. So there's an arrow visualized in front of you on the ground, and this is just showing how much of the time did you actually follow that arrow. And so in the prescriptive guidance case, we can see that there's an effect where the less people listened to the guidance in the arrow condition, the worse they did. So the longer it took them to solve the game. But that effect goes away in the combined case, meaning that they were making independent choices by not following the prescribed guidance, but they were still doing just as well on the game, which suggests that they found viable alternatives that still maintained a good progress and they were still efficient. And so this was something that was really, really interesting for us to see. So people solved the task quicker with combined guidance, but they were still productive even if they deviated from what the system actually thought was the best policy. So the sort of high-level takeaway from this work was that providing visual insights that were generated in real time alongside the robot-generated suggestions improved trust, interpretability, and performance. But what the ultimate effect was it empowered people to be more independent through this task. And so now that we saw that, well, people are independent on their own, and then giving them information actually empowers them to make informed choices that maybe deviates from what we expect while still maintaining productivity, we should start thinking about conditions where we might not want them to do that. And so I'll go to my last piece of research from my group today called Human Non-Compliance with Robot Spatial Ownership Communicated via Augmented Reality. And this is work that we're about to present at ICRA in London. And this is looking at robots from the perspective of robot safety systems in co-located environments, and in particular, warehouse environments. So we know that warehouse robots are neither legible nor predictable, meaning if you see a little bit of how the robot's moving, it's not necessarily clear what its goal is. And if you knew what the robot's goal was, it's actually not really all that clear that you're going to be able to know how it's going to accomplish it. And so this combination makes for a particularly perilous situation for a human that's going to have to operate in this environment. And we do manage to do this already, but we have a lot of structure around it. It's certainly not the sort of fluent human-robot teaming dream that we talk about quite a bit within the human-robot interaction community. And there have been plenty of foundational literature contributions and promising ideas along the lines of creating this kind of awareness so that people can understand what these robots are doing and act productively around them and safely. So whether this is using device-borne augmented reality to visualize robot paths, to visualize things around the robots themselves to give a better understanding of where they're going, or just providing environmental cues that are going to help people understand the goals and the mechanisms behind how autonomous systems might be operating. So we looked at these different systems and we said, well, none of these are really getting at this notion of safety critical behavior, and none of them are looking at this notion of compliance directly. They're just looking at these systems under an assumption that people are going to follow not just the letter of the law, but the spirit as well. So we designed an experiment using augmented reality to help visualize spatial ownership information for a co-owned space and enable bidirectional human-robot communication within this space so that the team could ask for permission to go to different places. They could divide up the space so that the robot has some spots that it owns, the person has spots that it owns, and formulate this in terms of a safety system. And what we really wanted to investigate was compliance and safety. So in our experimental environment, we had motion capture set up. The participant was building a Lego structure on a table. They had parts bins that they had to navigate out to. And during this, there was a quadcopter that was flying throughout the space. And we had two different conditions. One of them was a co-located condition where people went out onto the space with the quadcopter. So they were in close proximity to it. And in another case, the quadcopter and the person took turns occupying the space. So they were never on the space at the same time. Now, one thing that's interesting is that the experimenters had a safety net around them, and obviously the participants didn't, and nobody noticed this as something that was meaningful, which sort of contributed to our notion that people are dramatically overestimating their safety when they're interacting with these autonomous robot systems. So participants would be at their workstation, and they would follow instructions that would tell them to navigate to a particular bin, pick up a particular set of parts, and then come back to their home base and assemble them. And so we had them build a fairly complicated Lego structure that required a number of different ventures out onto the workspace floor. And this was meant to habituate them to their work environment, because obviously these participants aren't actually working in a factory or a warehouse. They don't get over this novelty effect of having a robot around them. So we tried to do the best we could. So the augmented reality safety system that we built, we called Fences, and it looks like this. It draws a grid on the floor that color codes who owns which space. And so blue squares were owned by the participant. You could safely walk through any of them. Yellow squares were not owned by anybody, and so neither the robot nor the human could go there. And red squares were owned by the robot, so you certainly couldn't go there. And participants were told this no fewer than 3 times during the experimental briefing. And so we built this system. Participants using this system could interact with it as like this. So in here, the person is requesting access to bin 6. We can see that the floor changes color. Before I muted it, you might hear the very loud quadcopter buzzing around there. And so they're walking along their path to bin 6 to pick up their parts, return back to their home base to continue assembling their structure. Now, because this is a human-robot interaction experiment, we couldn't just let everything go according to plan, especially because we were testing human behaviors surrounding compliance. And so partway through this scenario, we introduced something that we called the trap scenario. So if you look at the figure on the left side of this slide, see the person starting at home, and then they request a path to the far left side of the grid. And then once they get there, the robot changes ownership of all of the squares on the floor to be robot owned, effectively blocking the person from being able to get back. And we kept them there for about a minute before the robot actually gave them back a path to get home, just to see what they would do. And what was really impressive in a kind of a scary and awakening sort of way is that a quarter of our participants chose to trespass through the red and yellow regions to return home during this trap scenario, meaning they rationalized to themselves that it would be okay for them to do exactly the opposite of what they were briefed and to violate the parameters of the safety system. Whereas over half of the participants in total assumed that something had gone wrong, and they tried to engage with the system in some novel way. So again, over half of the people encountering this situation that was unexpected started mucking around with the interface, trying to fix some problem that they thought must have come up. And a quarter of the people did something that they were told explicitly not to do. So they violated the rules of the engagement by walking through spaces that they were told were unsafe for them. And so when we talked to them in the after experiment interview, we got explanations like, well, I knew I was faster than the drone, so like no matter what, I was going to be okay. Well, this drone runs a lot faster than they do. And they just didn't know that. And this other person said like, well, there wasn't a path, so I can see that it's safe. So I overrule the system, suggesting that given this information, people think that they're seeing the full picture. And if they can't immediately figure out why the system is telling them to do the thing that they're doing, they're going to make excuses for themselves and enable themselves to get themselves in trouble. Critically, everybody felt safe during this experiment, regardless of whether or not they were in the turn-taking or the shared space conditions. And we found that people even thought that the safety aspect of the system was inefficient. Again, kind of contributing to this notion that people dramatically overestimate their own safety when they're interacting with these systems. And so looking at our mixed methods analysis, we had really three important take-home points. So one of them is that people vastly overestimate their own safety and are willing to sacrifice their own safety to achieve increased efficiency, even though they're often wrong about how much safety margin they really have to give up. Second is that people need insight into why systems are doing things, especially when it becomes unexpected, because they were going to make excuses for themselves to kind of be independent and do what they want, and this might end up putting them in harm's way. And then lastly, something that we noticed, because we were tracking how often people looked at the robot as they were interacting with the scene, we found this effect that the more intelligent they thought the robot was, the less often they looked at it while they were actually on the floor. And so manipulating people's perceptions of how intelligent these robots are is going to have a meaningful effect on some of that overtrust and some of their behaviors about how they interact with and check up on these robots when they're co-located with them. So I'd like to conclude my talk with just a quick little teaser about some of the things that we're doing beyond these experiments to operationalize foundational robotics techniques by combining them with insights from these kinds of human-robot interaction experiments and algorithms. And that is building a smart cane for people with visual impairment. So we've had 2 papers on this already. So we presented this first one at this past AAMAS, where we were able to take traditional robotics techniques and embody them on a robotic cane to help people with social tasks, such as finding socially appropriate seating and navigation through both dynamic and novel spaces. So this is combining mapping, navigation algorithms, and insights from human-robot interaction research. And then a paper that we're about to present at this year's AAMAS that we're calling Shelf Help, which is taking the same kinds of techniques, but now using them to assist people with manipulation tasks. So when you have non-tactically differentiable things, so going grocery shopping, for example, a lot of products feel the same, trying to build more independence into people with visual impairments lives by automating some of the capability that currently requires manual assistance with other people. But the reason I bring these papers in at the end of the talk is showing that this is the net result of doing these investigations into these explainable and decision support related techniques, because this allows us to operationalize this into a very tangible use case that's applicable right now. And I'm also mentioning this because we're actively looking for collaborators on this project. So if this is something that's appealing to you and you'd like to join our team, I would encourage you to please reach out. So with that, I will conclude and be happy to take any questions.
Okay, thanks a lot. Do you have any questions? Are there any questions?
Can I go ahead?
Yes, sure.
So thank you for the great talk, Brad. I actually have 2 questions. So the first one is, I found very interesting all of them, but this very brief result that you just mentioned in the end about the gaze, it's very interesting, and it led me to think if, do you want to also manipulate the gaze of the robot so that you can affect the way people model their own perception of the robot's competence? And another question I have for you is, having a robot making suggestions to people and improve the way people do things generally, have you ever thought about the way it affects people's sense of control and agency on the task? Is this something
These are great
that
questions.
Okay.
So I'll try to do the best I can on this. So for the first one, I would say this really comes back to like maybe a perspective that I have, that I think we don't do a good enough job training people on how to interact with these systems. And so we kind of approach this from the perspective of like, we're going to investigate foundational aspects of human psychology and just how they naturally interact with these systems, right? So what's the sort of default behavior that people exhibit? And let's design our systems around that. And that is a good approach. But there are a lot of structured environments where we do have the opportunity to train people into sort of like better behaviors. And so in this case, like operating within the confines of a safety system in a professional and then thus potentially structured environment, you do have the opportunity to train people explicitly and give them sort of overriding guidance. And I think that kind of thing is going to be very powerful, certainly in the near term, especially because some of these results, like, well, people paid less attention to it because they thought it was more intelligent, makes sense, right? Like, we're not going to dote upon an autonomous system that we have trust in. And so maybe the question there is not so much like, should we make the robot do something that like forces the person to look at it, but in this case, maybe just build into their training that something telling them that here, like, this is just generally safe behavior, maintain situational awareness, take a look around. And I'm sorry, can you repeat your second question?
The second was about agency and sense of control.
Right. Yes. So I suspect that, I mean, this is something that comes up pretty often within decision support systems, right? Are you really just puppeteering the person, or are they actually making informed choices? And I would say the ideal situation is that we want people to bring in their critical thinking, because they likely have latent information that the system is not accounting for. And in fact, in some of the work that we're doing right now, extending upon this safety and compliance work, is looking at like collaborative trajectory optimization. So iterative design of optimization criteria between humans and machines. And typically what this comes to is, well, people don't include everything that they expected that they would, or they forget terms, they leave things out, and then are surprised. And so we're trying to figure out, well, how do we remove that surprise, and how do we come up with better optimization criteria? And I think if a system just told you, here's your optimization criteria, like, go with it, that wouldn't necessarily make for either a good user experience or an effective one. And so generally speaking, there's other research that shows that people are less concerned about authority so long as they're on a functional team. So people care more about being part of a productive unit than they do about being the one in charge of that unit. But of course, yeah, there's extremes everywhere. So if all you were doing is being ordered around by a robot, that probably wouldn't go very well.
Thank you.
Okay. Yeah, we have another question. Do you want to ask Mahak?
Yeah. Hi, Brad. Great talk. So I was wondering about the trespassing behavior. It looks very similar. I mean, it's in logic to jaywalking. So I think it would be like really interesting to, like, if you were to compare like jaywalking with autonomous cars and with like normal other cars and like with robots as well. Like, if that would be a study on, like, what do you think that's actually, like, if there's any correlations and so on?
Yeah, I think that's a great point. So there are these safety systems that are implicit, right, that we are kind of societally conditioned to ignore over time, because well, like, nothing bad has happened to me yet, or like, I think I can see when the danger is coming. And I think that's exactly what we're seeing here, is that people just generalize those experiences into new environments, but they don't actually have the basis for doing so. So for example, you have different dynamics in a warehouse environment with, say, flying robots, ground robots zipping around than you might on like a street that you'd be willing to jaywalk on. And so I would more liken this scenario to somebody choosing to jaywalk in front of a dark tunnel where you couldn't really see if the cars are coming or not. And so you might falsely generalize your experience that, well, like no car has come for 5 minutes. That probably means that there won't be another car for another 5 minutes, so I can just walk across here. But yeah, I'd be interested to see how that sentiment kind of maps onto that as well.
Yeah, I mean, like if you were to think about like very I don't know, rule obeying and cultures, like I don't know, Swiss, for instance, like they would never jaywalk. I don't think like I mean it's a perception that they wouldn't trespass when a robot when you said don't do it, whereas my culture, Turkish, we would definitely do it. So like it could be also like culture dependent. I don't know if you were like testing Americans and so on.
Yeah, and I think that signal is probably also modulated by how much you overestimate your own safety. And so if, for example, like moving with the traffic like analog, like if all of the vehicles were, very lightweight and made out of some kind of like soft balloon-like material, then, getting hit doesn't really have that much of a penalty. So you're willing to take that risk. And then you move somewhere else and now all the cars are made out of metal and they weigh thousands and thousands of pounds. You might assume that that's not the case because it clashes with your experience. And I think that's really what's happening here, is that the general public doesn't have an idea that's informed about how dangerous these systems are, how fast they move or how strong they are. And so they're using a faulty model to kind of base their decision making. And so one of these questions that comes up is like, how do we actually show them that in a way that's effective, right, without being traumatic?
That's what I was going to ask, actually. If you were to like show a video of a drone crashing to like a mannequin, at least not a person, then would that change? Like if you were to do a control experiment or so on, like would that change how they behave?
Yeah, so I would say that like you can go the other way too far on this, right? Like you don't want people to be terrified of your autonomous system. If we go back to kind of the premise that I started with about like responsible deployment of autonomy and like trustworthy autonomy, then I think it's less a case of, like we have to show people that they're going to really get hurt if they disobey us, because of course we want our systems to be able to accommodate, these like sudden shifts that might happen accidentally. But we also don't want people to just be emboldened to completely violate the rules, not necessarily because of safety reasons if we have intrinsically safe controllers, but just because that's going to prevent you from making progress on your task. And so I'm not entirely sure what the answer is, right, for briefing people and walking that fine line of balance between them. But I mean, this is one of our significant challenges as people that are amongst the forefront of putting robots into human populated spaces, right? Like we're still figuring out the like long tail of situations that we're going to have to explicitly account for.
One last thing. What if the robot were to say something verbally, like, what are you doing or something? Would that change the behaviors, or do you think would be better or worse?
So I think there's probably, some novelty effect that you can like achieve by having the robot, guilt or shame the person. But I think as at least we've seen in human-human interactions that one, some people are just completely immune to that, and two, people habituate to that, and then they kind of stop caring. So that's something that you'd have to deal with, right? That if these warnings never really have any teeth behind them, then people are just going to become complacent about the warning. And so now you've just maybe introduced a 1 or a 2 time use stopgap. You've hit the snooze button on it, essentially.
Okay, yeah, I think I have more questions, but we can discuss it during HRI anyway. Thank you.
Great.
So thanks a lot once again. Are there any other questions? I had questions as well. I think we have very little time, so I will ask the one that should take less time to be replied. When you mentioned interpretability and you say like make the system more interpretable from a human point of view, how do you measure that?
Yeah, so the only tools that we really have to measure interpretability is just asking people to tell us about how they thought the system behaved. and why they thought the system would provide such a recommendation, and then essentially looking to see if they were able to generalize the decision-making rationale of the system into new contexts. So there are a bunch of ways that I guess you could do this in a systematic or more structured way, right? You can give pictures saying, all right, here's the state of the system, like what do you think it's going to do? Or you could ask them to describe things that you could then eventually map into feature weightings, or even just features themselves and relative weightings.
Okay, so you measure the predictive capabilities of the humans based on what they like after the interaction with the robots. So if they were able after to predict their future behavior or possible behavior in different situations.
So that's part of it, right? And the other part, so getting to the correct prediction, but like using the wrong features doesn't tell us that the system was interpretable, right? Like.
Yes.
And so we need to so that's why we have to use essentially these interviews, right, to really tease apart which one they're doing, right? And so they might have found some alternative explanation that works just as well, but if that doesn't mirror the the feature weighting that the actual system itself is using, then the system was not interpretable, but it was maybe easily predictable.
Okay. I have other questions as well, but we'll also, I know it's late for you, so I think we should wrap up. So thanks everyone. I'm gonna introduce very quickly our next speaker. So can you see my screen once again? So here we go. So our next session will be on the 22nd of March, and we will have Saurabh Gat from Carnegie Mellon University, and he will talk about domain adaptation under relaxed label shift, and hope to see you all for the next session. So